Hi, David from Electric Teaching here with part 4 of our Midpoint and Simpson's rules with TI programming. And I just learned something. As a teacher, you always learn something, so I'm just going to share this with everybody. The programs that I've been writing will have a little bit of difficulty with irrational deltas. For instance, the delta we're using right now is pi, which is irrational, divided by 4, which is still irrational. And so there's a rounding issue, and I've been kind of hinting about don't round too early and stuff like that. Well, I believe the TI has a rounding issue. So I've tested, and the sum sequence program actually is accurate, and it was doing exactly what it was supposed to be doing. But when it tried to reach this last delta here, when it tried to reach this last increment of summing up the midpoints, what happened is that since delta was irrational, it never reached this last point. Probably, my guess is because of a rounding error. So I need to trick it. And on this note, if you liked my left in and right in points and trap points, I bet they're going to have the same kind of problem unless you do this adjustment. They'll work on all deltas that are incrementing that aren't in, like, for instance, trig world, where there's a lot of irrational inputs. But it'll work most of the time then, except for those irrational moments. But I have tested it, and it is because of the irrational part here and some rounding. So in a sense, I'm going to have this thing back up so it allows me to input this last delta, this last height right here. For this last height on the midpoint one, I'm going to have it back up instead of the full delta. I'm going to have it back up like 95% of this delta. So I'm going to insert 0.95, and I'm just kind of guessing on how much I need to do it, but I figured 95% of it would give me enough, probably 99% of it in a sense. So what I'm going to do is have it basically back up, not a full half delta, but 95% of it. So in a sense, it'll go in like where the blue line is compared to the purple line, which then when in the incrementing part of it, it will allow me to get to this point. So something I've learned there. If I run this program again, I'm just going to quit out of here now that I have it incrementing correctly. And you can see I was testing my left in and right in and trap ones, which I think have the same exact problem. I should fix those. If I test my program, I'm going to go run that calcsum2 program again. And now let's see if I get the 2.485 number coming out from 0 to pi with a delta of pi over 4, and it worked. Okay, so I learned something. Hopefully you learned a little bit too. Now let's go back to program. We're going to edit our calcsum2 program. We're going to edit our calcsum2 program. We're going to add in Simpson. Simpsons, I cannot use the sum sequence trick because the increments are not a simple delta. If you look, the increments are changing 4 times something, then 2 times something, then 4 times something. So I've got to be a little bit clever here using this formula in the programming. All right, so what we're going to do is we're going to use a for loop. And what I'm going to do is I'm going to sum up all the 4 multipliers, okay, and all the 2 multipliers, and then we're going to add them with the first and last heights that we're plugging and checking to get, and then we'll multiply by the delta over 3. Delta over 3, b minus a over n divided by 3 would be delta over 3. So that's how we're going to do this, and we're going to do this using for loops. The first thing I got to do is I got to zero out some variables, or initiate some variables at a 0 value. So I'm going to store 0 into the variable f, and I'm going to use the variable f to be all the sums with the 4s on the multipliers on the outside. And then I'm going to do the same. I'm going to do 0, store, and I'm going to do alpha t, and we're going to then sum up all the multipliers with the 2 on the outside. All right, we're going to do a for loop. So I'm going to go to program, and a for loop says basically for the increments of 1 to 5 or 1 to 10, incrementing by whatever you want, by 2s, by 1s, by halves, whatever you want. you are going to run a bunch of calculations, a bunch of iterations, as we like to call it in programming world, of in this case, summing up a bunch of increments with 4 on the outside and with 2 on the end, and 2 as well. So the way a for loop works is you're going to increment a variable, and I'm going to choose to use I, kind of an old school programmer, so I tend to use I and J for my increments. For I, okay, is the way this will read. For I starting at, what's our starting value? Well, our starting value is for the 4s, all the 4s, is A plus D. A plus D. So what we're going to do then is we're going to start it at, okay, the value of A plus D. But in a sense, that's what I'm storing into the X variable, which will be plugged into the function. So to do this, I think I'm just going to increment it starting at 1 and then use I as an incrementing of D. Hopefully that'll make a little more sense in a minute here. So instead of starting it at A plus D, I'm going to start it at 1 and increment just integers here. See, this D is an irrational number, and the for loop does not like to deal with anything but integers, especially irrational numbers. It will really make it upset. So what we want to do is increment I starting at 1, comma, going all the way out to, and let's see, with all the 4s, okay? So if we divide this up, I know I'm kind of not making the best sense at first here. It's hard to explain this again on video, so I'm doing the best I can. But if we divide this up into 4 intervals, we're going to have 2 multipliers of 4. For instance, when we did it earlier, we divided it up into 4 intervals, and we had 2 intervals of 4. And I've looked at it, and if we went out to 8 intervals, we would have 4 multipliers of 4. And it ends up being that whatever intervals we're doing, half of them were going to be, or n divided by 2, were going to be the amount of ones that we had by 4s, that had multipliers of 4s. So what we're going to do then is we're going to increment from 1 to half as many n's, alpha n divided by 2. And we're going to increment this by 1. So what happens here is this will go through the loop half as many n times. In this case, if n is 4, it's going to go through the loop for I equal 1, and then for I equal 2. 4 divided by 2 would be 2, and it'll stop there, and it increments by 1 at each time. If I did this 8, there would be 4 of those 4 multipliers. So this would go up to 1, 2, 3, and 4 being 8 divided by 2. Hopefully that's making a little sense. I think the more you do this, the more it makes sense. I apologize for not being explaining this perfectly right off the bat. Let's see, what are we going to do? We need to plug and chug an x value, and the x value is a plus d, and the next one's a plus 3d, and the next one's a plus 5d, etc., 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 as many as we need, depending on the n's. So that's what we're going to do. We're going to put in we're going to store into x the a plus, let's see, 1d, 3d's, 5d's. A little trick to incrementing by odd numbers is to using the I that we've created up here, is to multiply 2 times I. You might remember in some mathematics classes where you've learned to get odd numbers by multiplying, by doubling, and either subtracting or adding 1. In this case, if we subtract 1, then multiply it times our delta, this will increment perfectly on all the odd deltas, 1d, 3d, 5d. Check it out. If I is 1, 2 times 1 minus 1 is 1. So this will be a plus d right off the bat. A plus 1d. Then if I is 2, when it gets to the second one, it's going to multiply. 2 times 2 is 4 minus 1, so it'll be a 3d. So it'll be 3d. Similarly, with I is equal to 3, it'll be 5d, and this will give us each odd increment. Now we're going to store this into x. We're going to store this into x variable. And then what we're going to do is we're going to plug and chug this into the function, into the square root of sine of y. So in this case, the y1 function. And the way you want to do that is you want to call out the function vars, right arrow, function, y1, parentheses, x, parentheses, x. So this is why I'm incrementing with I just going through integers. I can control how the delta is plugged and chugged each time we loop through this for loop. So it's going to increment x to be a plus each odd delta. And then we're going to plug and chug it. And then we're going to store this into, well, we're going to add it, so I want to keep adding. So we're going to add this to the original f, or the next f, or the next f as it loops through. So we're going to add this to f each time and store it right back into itself so that it increments, or it adds to it. It sums up f by storing it right back into itself. We need an end statement, so you go back to programming, and the seventh one down is end. So this now will sum up all the 4 multipliers and put it into f. We need to do the same thing for the 2 multipliers, so very similar. I'm going to do program. I'm going to do a for loop, 4th one down. I'm going to still say from I. I'm going to reuse these i's because I've already used them when I need to get f summed up. So I can reuse them and start it all over again. So for alpha, I, comma, I'm again started at 1, increment this time. Let's see, how many times do I have to go up to get the 2? And so I've looked at the way the program works. There is going to be, for 4 ends, there's 1, 2. Okay, for 6 ends, there's 2 of these 2's in the middle. Okay, this is a kind of an example of what 6 ends would look like right up here in the original formula. Okay, so for 6, there was 2. For 8, there was 3. For 8, there was 3. And so if you follow that pattern out, you're going to see how many you're going to get each time, okay, is based on, hang on, I'm kind of looking it up, on basically doubling your, cutting your ends in half and subtracting 1. So for 4 of them, if we cut it in half, for 4 ends, if we cut it in half, that's 2, and subtract 1, we would have 1, 2 multiplier, and we did. For 6, if you cut it in half to 3 and subtract 1, you're going to get the 2 multipliers, or excuse me, the 3, cut it in half, so excuse me, 6 divided by 2 would be 3, and then subtract 1, you would get the 2 multipliers. Okay, so the number we're going up to is actually the alpha n divided by 2 subtracting 1. Okay, and we're going to increment by 1 again. We're going to increment it by 1 again. And so that's the way our for loop is going to go. It's going to go up to half the ends minus 1, and that works to give us the perfect amount of 2 multipliers in this formula. Okay, I'm going to hit enter, so everything in between the for loop and the end will be repeated until we've gone through all the i's that we've said we're going to go through. So very similar, I'm going to figure out the plug and chug of the x. Looks like the plug and chug of the x is a plus 2 delta, a plus 4 delta. Seems to be all the even deltas we're plugging in. So the way I'm going to do that, just like I did before, is going a, alpha a, plus 2, got to think about this a little bit. So 2 times I, that'll be an automatic even number, correct? An automatic even number. So 2 times I times the delta. So let's just write that straight out. 2 times I times the delta. So let's double check to see if this really will store what we need. I don't need these extra parentheses. I think I'm just being extra thorough here. So if I is 1, This is going to put in a plus 2d right off the bat. Good, that is the first one. If I is 2, it's going to be 2 times 2 is 4, 4 times d. It will be a plus 4d. If I is 3, it'd be 6d. I think it's following the pattern correctly. And as I stored this one into F, I think I'm going to store this one. Oh, excuse me, this is the plug and chug, so I'm going to store this into X first. So I'm going to put this value into X. You can see this is the X value going into the function. So now we'll sum up the functions plugged in with these X values as we loop through. So we're going to do the Y variable, vars, right arrow, function, Y1, parentheses of this X value that's changing as we loop through. Okay. And then we're going to add that to the original. I think we used T, right? We used F and T. I think T for 2 and F for 4. So we're going to plus alpha T, which starts at 0. And then we're going to store this right back into itself, alpha T. Okay. Now I'm going to put an in statement. So second program, excuse me, not second, but program, and the 7th one down is end. So now the second loop will sum up all the multipliers of 2 on these functions and incrementing correctly for the plug and chug part, the X values being plugged into the functions. Okay, so now I will have the first plug and chug, the first plug and chug of the formula. Remember, again, these are kind of the interior with the multiplier on the outside still we'll have to consider. So the first one is f of a. So I'm going to add that. I'm going to, do that right now. Y variables, so vars, y vars, y1 at a. Now plus all the 4s. That's all stored into alpha F plus all these 4 multipliers plus all the 2 ones so that's stored in alpha T plus plus the last one, which is the Y variable, so vars, right arrow, enter, and plug in the alpha B. So this is the entire interior for as many ends as you like, as long as the ends are even. Again, remember, ends have to be even with Simpson's rule. So we're going to store this value into just, I guess, S for Simpson's, or sum, I don't know. And then hit enter, and now we're going to display. So program, input, output. We are going to display, the third one down there, display the delta divided by 3, that's the same as b minus a over 3n. So the times the s. So let's do it this way. Let's do it alpha s times alpha d divided by 3. And I hope that gives me the Simpson's approximation, as well as above will give me the correct midpoint approximation for this formula. So the Simpson's approximation was 2.284 when we did it by hand. So let's see if the calculator is working with us here. I'm going to quit the program. I'm already in the program mode for CalcSum 2 here. So if I hit enter again, it should just ask for the A, and I'm going to give it 0 to pi, and again 4. And it should give me 2 answers. Uh-oh, I did something wrong. I'm going to have to pause the video and figure this one out. So give me 1 second here. Oh, quick fix. Hopefully you may have even caught this. If I'm going to do the 4 multiplier on the plug-in of the function, so you can see it right here in our handwork. So I forgot to put the 4 multiplier in there. So I'm going to insert a 4 multiplier in the loop that sums up all the 4 multipliers. Something pretty obvious, I think, but I slipped my mind when I was putting it in. And this one's the 2 multiplier, and so it's missing the 2 multiplier. And so this is why our sums were so low in our estimation. I believe that was the only mistake, so I'm going to quit it, try to run it again from 0 to pi with 4. And I get the 2.284768. Yep, I do. I get the correct Simpson's rule. I get the correct midpoint rule. And this is the conclusion of my fourth video in the midpoint and Simpson's rule. I'm David from Electric Teaching, and I hope that I have helped.